Hi, thanks so much for tuning into my very first YouTube video. I decided to make a YouTube channel because I want to review Kaggle contests. I frequently participate in Kaggle contests, and even if I don't participate, I frequently would just review the top solutions of a completed contest. And I figured that making quick little videos like this is a great way for me to cement some of this knowledge into my own brain. If you are not a programmer, this might be a little bit over your head. There's going to be some pretty code heavy stuff we're going to be going through here. If you are a machine learning experienced practitioner, hopefully you will still get some valuable insights here of what's going on in Kaggle, a bit of a survey of what's happening in these recent competitions. Anyway, let's, I guess, just dive into what I want to talk about today. So we're talking about this contest that just ended. It's called Enfit, Predict Energy Behaviors of Prosumers. And let's just read the overview. The goal of this competition is to create an energy prediction model of prosumers to reduce energy imbalance costs. This maybe even better, your challenge in this competition is to predict the amount of electricity produced and consumed by Estonian energy customers who have installed solar panels. So basically, people and businesses put solar panels up. You're kind of coming at it from the perspective of Enfit, which is the energy company, and you want to make better predictions of how much energy is going to be used by these customers and how much is going to be produced. So you can read the description and about Enfit. I'll have all the links for all of these notebooks that we're going to be, all these notebooks and pages that we're going to be looking at in the description. Evaluation is very standard, mean absolute error. This is extremely standard way of evaluating predictions or machine learning models or any kind of predictions. Submitting, this is a code competition, so all of the submissions to this must be through the Enfit provided API. Don't worry too much about this, but just know that it's a slight little pain in the butt, because when you click submit on one of these code competitions and they have like an API, it's oftentimes very difficult to debug your code. So if you're ever competing in one of these Kaggle competitions, you can kind of know that it's going to be a little bit of a pain, and just know to read the discussion forums, because other people I'm sure have had the same problems as you. I'm not going to be going through the basics of Kaggle, how to use Kaggle. There are plenty of other YouTube tutorials on that, so I'm just kind of assuming that you know what Kaggle is as we're kind of going through this. So I'm recording this on February 9th. The deadline for the final submission was January 31st. As I mentioned, it's a code competition, so basically you have to have your code submitted by January 31st, all of your models uploaded as a data set, and then the prediction timeline, as it mentions, so it's going to be April 30th is the competition end date. So basically you submitted your models January 31st. They have a public leaderboard of data that's like historical data. And then by the end of April, they'll have the private leaderboard. So here I am sitting squarely in the bronze medal range, hoping that my score doesn't deteriorate too dramatically to knock me out of there. So just fingers crossed from between now and April. Maybe I'll post an update at the end of this. Okay, so diving into some of the EDA here, one of the great or maybe bad things about Kaggle is if you wait like a week or two after a contest starts, folks will just post some really great EDA notebooks. So this one, just showing target over time, just looking at a couple different segments. Oh, sorry, I forgot to look at the data here that we were provided. My bad. Sorry. So so few data files. So the train file, right? This is the this is what you're gonna. This is the main file here that you're going to be training on. So county, this is the locality. There's only 15 different localities in Estonia. Business, that's basically, I feel like it's kind of like state in America. So is it a business? Yes or no. The product type, there's 3 different types of products. And then the target, this is simply your Y variable. So how much, is it consumption or production, right? So this person, right, produced 0.713 and consumed 96.59, right? The date time, so this is bucketed by hours. It's in Estonian time, so just a little bit of daylight savings, kind of mucking around, nothing big, no big deal there. Data block, row ID. What is the data block again? Just want to read it instead of trying to remember what this is. The data block, so all rows sharing the same data block will be available at the same forecast time. It's a function of what information is available for when, and the forecasts are actually made at 11 o'clock each morning. Okay. Okay. So this is right. So this is just a way of kind of joining up with the forecast data that they provide as well. Right. So row ID, just simple, index of what the row is. So this data set is not that big, right? It's only 2.02 million rows. And then prediction unit, as it mentions up here, prediction unit is a combination of county, is it a business, and product type. The other thing that it's a little bit interesting they didn't put is it consumption in there as well, because it's kind of each row is either consumption or production. So you have like one prediction unit and then 2 lines for each one prediction unit of consumption and production. Okay. The other data sets are gas prices. So this is just historical gas prices. Client. This is just reference data for the client. This is the most interesting thing here. How much installed capacity that they have. Basically, how many solar panels they have on the roof. Is it a business or is it a individual? Electricity prices, so historical electricity prices, 2 types of weather, forecast and historical weather, and then some files here for the API. Don't need to worry about that. Okay, moving along. Right, EDA. These plots are not that interesting. It's stuff that you would definitely have guessed, right? Basically you are making more solar panel electricity in sunnier months. That's really what these are looking at. And the next year you've installed more capacity, and so you're making more. What's sort of interesting though is kind of where it's the overall trend, I guess, is not that interesting. What is interesting though is where it spikes up, right? So, you have these little spike ups. It's basically just very much affected by weather, right? You have sunny days and you have rainy days, and these are just huge spikes up and down. Consumption though is a bit more interesting, because the spike ups, because you have a kind of an inverse here, right? It's sort of an inverse to you're making more solar electricity. In the summer months you have a dip, right? So you're not consuming that much because you're getting it from your solar panels. The spike ups though are frequently though around holidays, and so this was an interesting feature that was built to say, is it an Estonian holiday or not? So it's kind of a cool thing there. Same thing. Basically, this I think they have fewer, right? So the second segment, right, that we're looking at looks pretty much the same, except there's a lot more variability, and that can just be attributed to that they are fewer customers in this segment. So you have just bigger spikes and valleys. This is something very interesting that I definitely learned in this competition is fast Fourier transformations. I actually tried to figure out the math for this, but it's a little bit beyond me. But basically the intuition here for fast Fourier transform graphs are you can plot your data and see where your seasonality is. So here, right, this is nothing, there's nothing too earth-shattering here, right? We have monthly, seasonality, right? You're making more electricity in sunnier months, and hourly seasonality of, you're making more electricity in sunnier hours, right? Noon, and you're making more electricity noon versus midnight. Same thing with these other sort of EDA graphs of, more FFT transforms. You're, kind of seeing these things. But these, I just wanted to call that out in this video because it's just something interesting that I learned about, like, how to do more, a little bit better time series analysis. It's something that I just was not aware of before. Okay. So let's move on to actual like coding this. So this is my notebook, and this is, most of this is from public notebooks. I copy typically in Kaggle, or in Kaggle competitions. What happens is at the end of the competition, the last couple of weeks or month, people start getting private with what they're using for their boosters. Everybody's trying to gear up for getting a medal. And then at the end of it, like the last couple of weeks, Kaggle actually cuts off from being able to post public notebooks. So the game at that point is, taking a public notebook, taking the best scoring public notebooks, and figuring out where you can get a boost from it. This is, the game to get kind of like a bronze or a silver medal. Like the top of the leaderboard, those guys are kind of in a class of their own. But, for us, for us normal people, it's kind of, the game is figure out, these very good public notebooks that, if I were to be working and I were to produce something like this, I would be pretty proud of, but how to get something beyond them. So the intuition that I took was that the majority of public notebooks, they were all, first of all, light GBM. And the way that they were ensembling, they were ensembling 10 or so light GBM models together, but the only differences in their ensembles were just simply changing the random key. So my intuition was, first of all, I tried to do this with XGBoost, and I could not get XGBoost to score well. And so then I tried using CatBoost. So the best scoring by their own light GBM models, I think, were like around 67 mean absolute error. This is public models. For CatBoost, some guy had posted a public model, and his was something. It was not nearly as good. It was like 68 or something like that, but decent enough. So I took that model and I ran it through Optuna. And Optuna is a model, a library that simply goes through and kind of does a goal seek to find the best parameters, and it's used frequently for like hyperparameter tuning. So I wanted it to go through different objectives. Just kind of trying all this stuff. The joke here is, or the punchline here is that root mean square error was the best for consumption. Poisson was the best for production. Quantile and log quantile were just total, did not work at all. Oh, and Tweety, for some reason, CatBoost on GPU has some issues with Tweety, and I just couldn't get it to work. I probably should have switched to a CPU version of CatBoost. But I also just kind of, Tweety and Poisson are very similar distributions, so I just kind of skipped doing Tweety. The intuition here is, Poisson is basically looks like a big spike at 0, and then you kind of get a normal distribution afterwards. And Tweety is very, very similar. Right. Okay, so that's Optuna, and that's how I figured out how to get a different something different from everybody else. All this code down here is the same from the public notebooks. This is worth mentioning. I like how this is organized. just using a class for data storage, quote unquote data storage. This is basically just pulling in all of the CSVs as they were given. Another thing to mention, we are using pollers. So pollers is, if I'm sure everybody who's watching this video 15 minutes in is aware of Pandas. Pollers is basically Pandas written in Rust, and it's like probably 3 or 4 times as fast depending on the size of your data set. And I was just totally amazed. I'd used Rapid's CUDF before, which is basically Pandas for GPU. Pollers, like, I don't know if it was, I didn't do a benchmark to determine which one was faster in this particular data set, but man, this is like, I tried using Pandas first, and this is just, it was just such a huge boost in speed. The similar to CUDF, pollers, they try to do a lot of the same API, right? So, read CSV, right? The same thing as Pandas. Columns, they do things that are like slightly different, right? So columns, in Pandas, you'd say use calls as opposed to saying columns, for whatever reason that was changed. Try parse dates, it's Pandas, you have to say parse dates and actually tell it the columns, little things like that. Anyway, use ChatGPT to write these functions if you're just new to using pollers. Like it's really really first of all, ChatGPT will help you and make things way easier, but it's a great library that you should definitely get to know if you haven't been using it already previously. Okay, so the data is loaded. So the feature engineering class, this is just another class. I like, again, like this is, I typically don't organize my feature engineering like this. I'll typically just write like a simple function, but I think I might switch to this method because I really like how this is organized. Anyway, basically we're just doing all basic machine learning stuff here, right? So here we're just exploding out the dates, taking the date time and just making it an hour, weekday, year columns. There's a couple of features here that I think are interesting that I wanted to call out. Where is it? Oh, I think I scrolled past it. Yes, here. So these couple features here are taking the sine and cosine, so multiplying the day of the year and the hour, and then taking the sine and multiplying it by pi, and then dividing it by half of the value, right? So 183 and 12, and taking the sine and cosine of that. And the intuition here, right? I made a little spreadsheet to kind of show the intuition here. So these are these rows are going to be the resulting features that you're going to have. So if you look at like hour is 12, right? The sine and cosine are going to be 1, after the hour times pi divided by 12, right? And then taking the sine and cosine of that, because, right, so, the hour, that's going to wind up being pi, right? Sine and cosine of that is going to be 0 and 1. If we look at 23, right, that's going to be sine is, negative 0.2588, and cosine is 965. And the intuition here is that we're trying to get is, sine and cosine are, if you remember from high school geometry, of like the the sine. I don't know how to explain except that a sine wave is a sine wave and a cosine wave is a cosine wave. But imposing these values, it shows how cyclical it is, because 23, the hour 23 is very close to the hour 1, right, in terms of sunlight production, right? So then you get these two features here, right, which will be very close. It will kind of show the cyclicity. Same thing with day of the year, right? So 365, right, is going to be very close to, look at what sine and cosine are here, and it's going to be very close to 1, right? It's actually the same thing as 1 on the cosine, right? So point being is that you have these values that are going to be close together, to show the cyclicity of something like sunlight production, solar energy production. Okay, sorry, we're kind of don't want to spend too much time going through this stuff. I want to get to the meteor stuff. What other interesting features? Oh, of course, so basic time series stuff, right? Lags, diffs, things of that nature. So lags, right? We're looking at the most useful features here, like what happened yesterday at this particular time, what happened 2 days ago. Diffs are like what happened between the two different hours, hours today and yesterday. Target features. Oh, and then target features, right? So rolling averages, rolling standard deviations, rolling sums, things of that nature. These are all just, if you've done any time series stuff before, this is all extremely standard stuff. Basically, in a time series problem, you have the historical data, and you're trying to predict what's going to happen in the next time instance. In this, we're trying to predict what's going to happen in the next hour. So the features that you build are, the average up to that particular time, and then you're going to try to predict the next particular time, the next block of time. You do the same thing with standard deviation. You can do the same thing with sum, but that's very, very standard time series stuff, especially particularly for one-step time series, which is what we have here. Okay. All right. So now we're getting down to. So this is the bunch of parameters that I mentioned that I extracted from Optuna. I just took the top like 12 or so. I weighted it in a kind of hacky way by just simply the best scoring model. I just simply put in there 3 times with different random seeds, just so it would be slightly different. But that's just wanted that to be weighted. I probably could have done this a little bit better if I had done a better cross validation scheme. I didn't. I was just doing this kind of quickly and just wanted to get the submission put up. And then making sure that I had a good variety of different methods from the model. So the consumption, right? As I said, root mean square error was the best loss function. Poisson was second best, so just having a mix of just a little bit of the two, a little bit of Poisson, mostly root mean square error. The reverse true for production, mostly Poisson was the best model, and then root mean square error at the end for a couple extra little models. Loaded them all up, and then this model by itself did not score well. It was only getting like the best scoring models, public models at the time, I think were something around they're definitely around 65 mean absolute error. This model I think was getting 68. However, when I ensemble them together as I did in this notebook. So trained them in this. So got all the models. So this notebook tuned all the models, then I trained all the models, and then saved all the models. So save them in a data set, that I can then access from the submission. This is actually my main. This is my main submission notebook. So this is pulling from, if you look at the input, I'm not going to screw that up. So if you look at the input, this is the data set, that the output of pickle files from the huge ensemble of CatBoost that I put together. So the way that this notebook works for submission, right? So when you hit the API, you expect to get in all of this test data, and you have to have your feature engineering stuff ready to go. So that's what all of this code is doing. So it's basically the same code for training. We're just calling again that I just basically copied and pasted that we will call in training. And fortunately, the API has a lot of new data in it, and they made sure that you can test it, so that these will, if they're running well and not producing any submission errors, will actually run in production when we actually go to test them out. Right. So the only thing that's interesting here is just weighting. The weighting, how I wind up doing the weighting here. So simply just taking. So this is the this is the best. So these predictions are the best scoring light GBM models, and then I just weighted that with 15% of my my trained CatBoost model. This is the things that I commented out. This is publicly available CatBoost models, which I was outperforming. So, I could have maybe done a little bit better here with fine-tuning this with a better cross-validation scheme and using Optuna, something like that. But I also was shying away from that because I don't want to, because I want more diverse models. I mean, I don't want to just only be having light GBM. And I guess I'm just trying to ensure that I don't fall dramatically down on the leaderboard. That can, hopefully this will protect me from overfitting. Will it? I don't know. Only time will tell, and just gotta kind of cross my fingers and hope that it works out. Okay, so this scores, like I was showing you, in the bronze medal range, like something like, I think my final score public leaderboard was, it was 63.54. So moving on to this notebook, and this guy posted this. I just really, I just really love this. Some of the stuff that he did here. This is a silver medal notebook, at least publicly. He's getting like 61. His or her. Sorry, I don't know if it's him or her. The big intuition here is that adding a whole bunch of features that I just didn't think to add. Just so many different features that he put in, mostly like lag and difference features and things that I can't really find it. Oh yeah, right. So he could have been way cleaner with this code, but this should have been in a for loop. But anyway, just all these just dividing stuff and just combining and like doing all of these just so many different features that were added here, and I don't think any one really gave him a giant boost. Oh, but well, true. But so what he did, after adding all those features, is did what he's calling a forward feature selection. And so instead of just adding all of those features that he added to his predictor, what he does is he's got this for loop, right? And in this for loop, he's taking all of his columns and he's going through each column and just adding it one by one. And if the column improves the score of the model, then it's added as part of the column. Then he's going back and he's going through every single column and looking to see if they improve his score. And that's what this internal for loop is doing. Now, that is in if you notice, it's in a while true loop, and the while true loop is taking all of the. We'll go back. So after the first pass through, we'll have some extra columns that weren't added in. And we're going to go through all of those columns that weren't added in and see if they have any interplay with the columns that were previously added. And then the break is simply if, at the end of that loop, at the end of the while true loop, if you haven't added any new columns. The structure is just like, it's such an elegant little piece of code, I think. It's something I'm, gonna absolutely steal and use in my own future work. Anyway, this is just a nice little idea from somebody who got a much better score than I did, at least on the public leaderboard. Okay, moving along to the top of the leaderboard. So So the third place solution and the first place solution that are currently at the top posted these threads in the discussion, and just going through them. So third place, so light GBM models with L1 loss. So this is I'm interested to see his see what he did here. So L1 loss is a regularization. So I'm kind of wondering how severely he set that. I just want to look at what was happening there. But yeah, he didn't do what I did, right? He simply used the same. Oh, he or she. I'm sorry, I keep saying he. I think this is a he, so I can say he. So he just simply used the same hyperparameters for both consumption and production models. So just retraining it every 7 days. Right, we're getting new data in from the Enfit folks. So ensemble 2 models together. Oh, this is his difference here. So so one was trained with target as is, and then the other one was trained with target minus the mean. So basically, and then target minus target mean plus 187. Oh, right. So basically, he's normalizing the target over the mean. So an interesting thing, I saw some people doing the difference. So taking the target, so trying to predict what, instead of the actual target was going to be the next day, trying to predict what the percent difference was. So that's another approach. But anyway, he took this approach and it was successful for him. So just 50-50 weight. I mean, and just just only 2 models here. I mean, just did 2 models and that was it. And not that many features either. So the outcome was 90 features for consumption, 77 for production. So really elegant approach. Really would love to see the actual notebook that he used here. This is more interesting though. So what didn't work for him? So gated recurrent unit. So the number 1 guy said that actually this did work for him. So he couldn't get XGBoost to work. He also couldn't get CatBoost to work. Again, light GBM seems to be the best gradient boosted tree these days, at least on Kaggle. It's just absolutely smoking XGBoost and CatBoost. Let's see. Oh, this is interesting. This is a library that I'd never heard of before he posted about it, but it's a if you go and look it up, PVlib. It's a solar related feature library, and he said that he got a bit of a boost from that. I'm sorry if you're hearing those sirens out there. I'm recording this from New York City, so I'm on 2nd Avenue. It's a bit of a busy street. Oh, right. He also posted this great notebook here. It was like a really great starter notebook. Really, really good. Okay, and finally, finishing off this video with the number 1 guy on the leaderboard right now. I don't know if this is I believe this is a guy. This is HYD, who is Super Grandmaster, number 15 currently. Just this person's work has just been something I've been following quite a bit. It's just really, really great stuff. Anyway, their post is so 4 XGBoost models. So 2 for targets is consumption. Oh, and 2 GRU models for 2 targets, right? For 2 targets times 2 is 2 consumptions. I'm not sure he's saying that. Oh, with 2 targets, 2 is consumption. Right. So difference between consumption and production. Let's see. So he or she wound up with just a ton of features. Merge all the tables and creating a lot of lag features. Didn't cut down, just created a just ton of features, and that's what gave them the boost. Again, everybody's using polars. Polar PL is polars. All right, so target features, right? So target minus 2 shift divided by installed capacity. So these combination features are really what I think separated a lot of the. It's kind of my takeaway here is the target features, the combination of target features, and how folks did this is really what separated them from the people like me and the public leaderboard. Yeah, he said, I didn't even spend time to tune the XGBoost model, just simply train and predict. So, yeah, this GRU model. I've never used GRU before, so I'm totally surprised that worked as opposed to why he used that as opposed to LSTM or something other like that. Yeah. So what didn't work for him? Solar features, transformers, didn't work for him. Multi-day input instead of single-day input, and split into more models given that business day is equal to 0, 1. Yeah, that's interesting. Anyway, yeah, cool. Basically, I got 7, under 100 features in this guy, or in the number 3 guy. This guy, just kind of shotgunned a lot of features. But yeah, this is, I think, the big takeaway here, the differences in his target features. All right. Thanks again for bearing with me in my very first YouTube video. If you've gotten this far to the end, extra special thanks. And hope you learned some stuff. Leave some comments if you enjoyed it, or if you didn't enjoy it, I guess leave some comments too. And thanks so much for tuning in. Have a good one.